Hi everyone and welcome to this week's Pilz Automation Machinery Safety webinar. I'm Jamie Thomas and I'll be your presenter for today. My colleagues Mark Staples and Jason Reed will be answering any questions you have via the tools section, the question section on the right hand side of the toolbar. So today we're going to be covering safe robot applications and in particular human-robot collaboration. A link for today's recording will be sent to the email addresses you registered with, and a copy of the slides can be requested again within the questions section of the toolbar on the right. So if any of you can't hear me, then if you could let us know and we'll all get started. So we're going to start with a brief history lesson on robotics. So for anyone that isn't aware, KUKA developed the first industrial robot in 1973 and called it the Famulus. So initially robots had to be fully guarded and no access was permitted unless the power had been totally removed. But as they got more freedom due to technological advances in intelligent sensors and with the robot itself, the robots evolved to include things such as protective inputs and e-stop inputs, and this allowed signals to be removed via interlocking devices or guard doors, light curtains, floor scanners, etc., and more recently radar. So this allowed improved interaction with the robot for both humans and products or workpieces. So until today we're not allowing at times total interaction in specific applications, but these applications are classified as human-robot collaboration. So what is human-robot collaboration? The scenario where people and robots occupy the same working area and can come into contact with each other is the first thing which comes to mind. However, it's not the only definition of the term. HRC covers many operating principles and methods, and Cobots can be used in a large number of different applications. So HRC is not one specific application. It does not describe a specific manufacturer. It can be any manufacturer and various operating principles or methods. So what is the meaning of Cobot? So a Cobot is a robot capable of collaborative applications. And you may be able to initially identify them as they look very different externally, as they're designed with no sharp edges or trapping points between the axis movements. And generally they're smaller in size due to only being practical in lower payload applications. And this is due to the force and pressure measurement allowances that we'll come on to later. But it's inside the Cobot where the big differences are. They have inbuilt sensing capabilities and intelligent safety functions, and this is how they detect these collisions. So when deploying a Cobot into an industrial application, you are making or completing a machine and therefore required to follow the UKCA or CE conformity assessment procedure. Depends which when you're doing the application. So to do this, you must comply with the HSRs, and as per the Machinery Directive or the Supply Machinery Safety Regs as of this year, you carry out a 1200 machinery-based risk assessment. And for those that don't know, ISO 12100 is the only A standard within the pyramid of standards under the Machinery Directive or the Supply Machinery Safety Regs. So within this, you will need to apply the C standard as well, 10218 Part 2. And using Annex A of this standard, there's a list of common hazards. But also particular attention needs to be given to Chapter 5 and the use of the 4 methods. And we'll cover this in more detail later in the presentation. But as well as the C standard, there's other applicable B standards. So to name a few, you'll be looking at 13849 Part 1 for safe parts of the control system, 13855 positioning of safeguards, 13857 for safety distances and the calculations within this. When you're validating the application, you'll be using 13849 Part 2, and in conjunction again with 10218 Part 2. And Annex G of 10218 contains a list of more than 200 points to give guidance on the requirements for the validation of the application. So there was a technical specification, TS 15066, created for HRC. And although it is only a technical specification and not a standard, it follows the usual format of a standard, and it's split into 7 sections. The format would be 1.1, the scope. So this is detailing what it covers. Section 2 will be reference to other standards or norms, as they're called. And in this, it references 10218 Part 2. Section 3 is your index or glossary. So it gives you definitions of the terms that might be in there if you need any clarification on them. Sections 4 and 5, these are the technical details for design and hazard identification, and also other requirements. So in this case, it will say that the performance level requirement is a minimum of PLD Cat 3 for the safe-rated parts of the control system. 6 will be verification and validation requirements. And 7 is just information for use. The annexes in the back will contain informative information, so that's information to help you, or norms or normatives, which are must follow requirements. So within the standard, it defines a number of spatial parameters, and they are as we have listed on the slide. So if we start with maximum space, this is the unlimited movement of the robot. So it's the maximum reach of the robot and the end effector complete with the workpiece. So it's the full reach when it's its maximum extension without any limiting measures. Then we move on to the restricted space. So this is where the robot is permitted to move following the implementation of limits. And they may be physical mechanical stops, electrical control devices, and is now more common today with advanced robots is safety rated software. Within this, guarding is actually allowed to be classed as a restricted spatial limit, but it's not common. And we'll come into more detail on that in the next slide. But yeah, it's not a common form for restricted space. And then there's the operating space. This is where the robot will maneuver to perform the task it's being designed and deployed to execute. It is not, as the previous point, restricted to this space, however. So it can go out of it, but this is just where it's expected to operate by design. So the safeguarded area. Safeguarded area is ideally outside of the restricted space to avoid the robot coming into contact with the guards. But if the guard is deemed to form part of the spatial limit, then it will need to comply with section 5.4.3 of 10218 Part 2. And the results of the risk assessment should be used to determine the requirements for the guard design, strength, and deflection. There's 4 notes in this section also, and particularly relevant is note 4, where it says, using a perimeter guard as a limiting device is normally practical only when robots cannot cause hazardous deformations to the guard. So basically what it's saying is the guard must be capable of withstanding the force of the robot. And when you think about some of the forces that are applied and generated by these robots, they're going to be a pretty strong guard. So it's probably not practical to do this. And finally, the collaborated space, the collaboration space. This is within the operating space, and this is where the human and robot contact can occur, and where both will interact and work together to carry out the tasks that it's been designed to. And this is where the validation tests will be performed, and we'll cover that later in the broadcast. So 10218. Just to note to start with that 10218 Part 1 is we're not going to be concerned so much with that today, but that's for the robot itself, and therefore is designed for the manufacturer. So the Kukas, Phanox, Yaskauas of this world. What we're going to be looking at is Part 2, and this is where the responsibility for the complete machine application lies, and it's generally for the integrators. So Particular attention should be given to Chapter 5 for the required performance level, as mentioned before, and some of the other key information in these points are from 5.2.2, for instance, where it says the minimum requirements of the safe-related parts control system of PRD Cat 3. But 5.2.3 says it doesn't mean that this is limiting. A higher performance level could be required if the risk assessment deems this is the requirement. So you may need PLE. Also, risk assessment, you may be able to justify that a lower performance level is required, or that you can't meet the requirements, especially if the robot can't meet this. I know some of the early Cobots released only achieved PLD Cat 2 for the collision detections. But again, you've got to justify this and document this in your risk assessment. So section 5.11 also discusses collaborative robots and the use of the 4 methods, but it doesn't give the guidance on the force and pressure limits, and it does make reference to 15066. And the 4 collaborative methods, we'll come on to them in more detail. So for those that aren't aware of how we get to performance levels, and many of you probably are, this is the risk graph from 13849. And if you follow the lines down, you'll see where we get to D. So to be at D, you must have selected S2, which is a severe injury. And these are mostly going to occur if you come into contact with a robot. So if you've selected a severe injury, you only need to say there's either a high frequency of exposure or the possibility of avoidance is scarcely possible. Then you will end up at D. And again, as we said previously, if you deem both to be the case, then you will end up at E. So it's not out the realms of possibility that that's going to be the case. So that's the performance level bit. The category of the architecture, as you can see here, we have 4 categories, 1, 2, 3, and 4. And we're going to be looking at Cat 3. So this gives you a single fault tolerance. And it means a single fault cannot lead to the loss of the safety function. So it offers you a dual channel architecture. So it gives you redundancy. And some may argue that you can achieve PLD with Cat 2 architecture, and in some ways that does give you redundancy, but it only actually happens following the detection of a fault and a secondary reaction. So this will mean there'll be slower reaction times associated with parts of the control system. So if you were to use this in any application, even using electrosensitive protective equipment, light curtains, as we've got in our diagram, then to truly calculate the stopping time of the machine, you would need to introduce the fault so that the system can detect it, process that detection, and then send out the reaction to stop the upstream contactor or the secondary device which would be used to kill the power. And then that would have to be used in the calculation in 13857. So US equals K times T plus C formula, and that would be your T part of that. So as we said, we'll come on to the 4 methods as well. So it says section 5.5 of TS 15066 discusses the use of the 4 methods for robots to work in collaboration with humans. And these are referred to as operations actually in the TS, but they're also known as methods as well. So you may hear both terms being used. But the first 3 are traditional in robot applications. It's only method 4 that's really new. So if we cover these methods, number 1, method 1 is safety rated monitored stop. And this is where there's no contact allowed with the moving robot. And this is generally achieved by guarding or protective devices. The robot must have come to a safe stop before entry is allowed. And it can be any stop category, 0, 1, or 2. They're all possible, but just depends on the application. And this stop would usually be triggered, as we said, by guarding or scanners or light curtains. But the scanners would also, or radar may also be used to monitor the collaborative space for occupancy detection, because we need to make sure that it's not going to restart. Method 2 is hand guiding. So following that safe stop that we've achieved in 1, you may control the robot by hand. and this would be done by disengaging the brakes. But to disengage the brakes, really, it needs to be done from a 3-position switch. And the use of the 3-position switch is key to allowing the robot to operate through the hand guiding. It should be part then of the robot controller. And this 3-position, as you can see, is the middle position where it activates it. So if you let go or grip tighter, it won't operate, won't give the OK signal. So some of the requirements that need to be considered as well, again, the performance level. So we've got to think about that, PLD Cat 3, and safe speed limiting maybe, and the other safety functions of the robot. Method 3 is the speed and separation. So again, still no contact with a moving robot, but it may be that it's unguarded and the human approach is detected by sensing technology to slow the robot down, maybe in the sort of amber zone. And when you get too close and you enter the red zone, then the stop is required. And so you may be, again, looking at scanners, radar, or something like that to carry out these requirements. But only if them devices will achieve performance level D category 3. And you then have to consider your stop performance. And so you time these stops to make sure that you still can't reach the robot and create an unsafe condition. So method 4, the new method. It's the first time it's been allowed for the operator and the robot to inhabit the same working space, and contact between them whilst performing duties or performing this task together. So we have to consider intentional but also unintentional contact. And there are stated thresholds for both force and pressure limits that are detailed in 15066, depending on the body contact region. And these must be validated, and the validation must be performed to prove there's no injuries that are going to occur in this mode, but also documented as well, so there's traceability. And we cover these 4 methods, and they're not all mutually exclusive, so you don't have to use one or the other. For some method 4 applications where you want to have true interaction with the robot, it might be that due to the speeds required to meet the thresholds in the force and pressure requirements, you can't go fast enough to get your throughput for the application. So it might be there'd be like a method 3 or method 3, method 4 collaboration. So it may be working at full speed, but you detect somebody coming into an area, and then you reduce down to a speed that will allow you to realize these force and pressure limits. So there's ways in which you can get to having collaborative applications that aren't just so black and white. So for a safe robot application, there's a special path. And why do we need a special path? Well, all robot applications do, but the validation requirements change, especially with HRC applications. So as with all machinery installations, you must demonstrate conformity to the law, and whether that's the EU directives or the UK regulations. You'll most commonly do this via the application of harmonised, or now under UKCA, designated standards. These standards are guidelines, and it's not mandatory to follow them. However, a lot of the working out has been done for you. They give you guidance, and they give you a presumption of conformity to the directive or regulation. And if you don't follow them, you have to demonstrate why what you have done is as good, if not better, and all the working out to prove that. So for me, it's kind of just common sense to follow the standards. Somebody else has already done that work for you. And whether you're UKCA marking or CE marking your final application, the process at the minute as we stand is currently the same. There's some terminology changes that you have to consider, but things like the HSRs, the standard numbers are the same. So it's just generally down to terminology changes at the moment. But to complete this, you must consider all other relevant directives and regulations, make sure they're met, and along with the EHSRs. So we will have the machinery directive and the supply machinery safety regulations, depending on where this robot's going to be. But other common directives considered are EMC, which as of this year under UKCA is called the Electromagnetic Compatibility Regulations, very similar. But the LVD, the Low Voltage Directive, is called the Electrical Equipment Safety Regulations. And these have always existed, it's just we're referring to them now as they're not previously called under the Machinery Directive. So, according to the Machinery Directive or Supply Machinery Safety Regs, a robot is classed as a partly completed machine. And this is due to the actual definition of a machine being that it's an assembly of parts, at least one of which moves, which is fitted or intended to be fitted with a drive to perform a specific function. And out of the box, a robot doesn't meet these requirements, as it will not perform a specific task until it's programmed and has an end effector. And this is why you won't see a CE or UKCA marked robot directly from a manufacturer. This is the integrator will do this. So the integrator is concerned with 10218 Part 2 and the complete machine, as we previously mentioned. And this is where they will give it an intended purpose or an intended use, and therefore effectively become the manufacturer. And the manufacturer will hold the responsibility for the safety for the UKCA or CE marking conformity assessment procedure. And within that, producing all the supporting documentation and issuing the CE plate and signing the declaration of conformity. The only time an integrator wouldn't do this is they appoint somebody else as an authorised representative to carry out these duties. And they will be doing the assessments, etc. Co-sign a declaration of conformity under mandate from the integrator and supplying the CE plate then, featuring both logos. So some of you that may have used us for services before may be familiar with the Pilz machinery life cycle. Our normal life cycle would start with a risk assessment before producing a safety concept, and this serves as a basis for the safe design. And then we go on to the safe design, the validation, the verification, etc. But what are the differences with an HRC application? Well, we introduced the application analysis phase, and this is to be done even before purchasing the Cobot, and it should be at the conception stage of the project. And you want to consider things such as, is it necessary that the application is collaborative? What is the requirement of the application? And what are the materials being handled? Because we've worked on applications in the past where doing this analysis too late meant that it wasn't possible to make, or financially viable to make, the application collaborative. And it wasn't to do with anything with the programming or any of that. It was just to do with safe design. There were sharp edges. The robot could have been placed in a different orientation. How it handled the workpiece could have been slightly different. And it's identified early enough, they could have all been designed out or just designed differently. But again, it was too far down the line and was not financially viable, so they ended up going with a method 3 application. So following the analysis, we do a risk assessment, and this is always the basis for any CE marking or any application where you're installing machinery. It's got to be driven by your risk assessment and following the standard 12100. And you'll do the normal things such as looking at the limits, tools, variants, there's operating modes, what's its intended use, any foreseeable misuse, and other activities. But also think, as with the application I just mentioned, the workpiece has an influence on the hazards. And this is something that needs to be considered early. So if there are sharp or hard edges, how it needs to be twisted or turned or transferred from one place to another, these need to be considered. But with HRC, even the path of that the robot moves and the axis rotations can cause hazards. So you may want to think about making sure that if it's placed on a worktop or near a floor, that there aren't any trapping points between the floor or another object and the axis movements of the robot, and you may move it in a slightly different way, and it will just remove these hazards altogether. But consideration has to be given as well, and documented, for a matter of fact, for the other collision types and expected body areas to be involved. You also have to think about an expected startup, because when the robot's standing still and people are in there, it's always got to be in a safe stop, but we need to know that it's not going to restart, especially if we're going to be working so closely with the robot in these collaborative applications. So following the analysis and the risk assessment, we'll move on to the safety concept. As I said, this will serve, if we produce them as Pilz, is a product neutral basis design. And we'll utilise the hierarchy of control, the three-step method for the risk reduction. But we'll also consider things such as safe distances, any applicable standards, safe-related control functions, sequencing, etc. And this is how we will reduce these risks down to the manageable risk levels or acceptable risk levels. So for those that don't know the three-step process, the first step, and again, this isn't just for robotics, it's for any application, is inherent safe design. So can we design these hazards out? As we said before, you know, taking out sharp edges, moving the robot in a specific way. There can be lots of different things that we can do. Then when we've gone through that, for other parts, we'll look at the functional safety and safeguarding. So do we guard areas? Do we use safety related controllers? Do we use scanners? But this is also where the safety rated software within the robot and the sensing capabilities and things like that can be used. And finally, and only when we've resourced these first two, can we go down the route of training, procedure, PPE, and user information. So, but also in this, for collaborative applications, you have to give considerations to removing lost work pieces in the operating manual and other instructions that you may need to interact with the machine. So following all that, then we'll come on to the engineering. So using the information gathered in the 4 previous steps, we'll do engineering design, installation, integration of the safe solution. And now the bit where it really changes and gets interesting for HRC, validation. So there's new processes and requirements introduced for HRC applications. As we said, we've never previously allowed humans to come into direct contact or interact with a moving robot. And as it's never happened before, it's never been considered before. So there was new requirements developed to validate your application. You must simulate these collisions and document the findings. And you must also cover both force and pressure. And this must be done to validate, as we say, the application. So why must we do collision analysis? So contrary to what some people believe, a Cobot is not safe out of the box. So yes, they have the force and collision limits in the fail-safe section of the robot control system, but they cannot solely be relied upon to ensure no harm is going to come to an operative, as it doesn't take into account dynamics. And when a collision occurs, what will happen is that the robot will realise it has come up against resistance and initially apply more pressure until it decides, wait there, I need to stop. So the force and therefore pressure will increase momentarily. And this reaction of increasing the pressure and then deciding, wait there, this is the point where I need to stop, and then reducing that, has all got to happen within half a second and without exceeding the deemed limits dependent upon the body area, as per the body map, which we'll come on to in a minute. And again, just to reiterate, you must document to prove these limits are not exceeded during this collision. So, without a risk assessment, there's no comprehensive, it's not possible to really do the measurements because we have to document them and all collision scenarios should be listed within your risk assessment so that the collisions can be and will be replicated. And to replicate the specific collisions, a device capable of measuring the force and pressure is required, and it must also be capable of representing the different areas of the human body. So if you have a look at the diagram, we'll talk about how you would replicate a collision. So point A in the diagram is where the movement will start, and point C being where it's programmed to finish. Point B, which is in the middle, is where the load cell will need to be placed in order to stop the robot mid-movement and accurately replicate a collision. So this must be documented as well to show and make it reproducible, so we can prove afterwards that we've done these calculations. But then there's a couple of different collision types, and these are the things we have to consider. So the first one we'll cover in this slide is transient collision. So this is where the person can recoil or retract if contacted by the robot. You can move away, whether it's knocked away or by reaction. But the key point is that they're not clamped. There's nothing trapping them. Whereas the second one is the quasi-static collision. And this is where you are clamped between a static or another moving part of the robot style. So we'll come on to the body map in a minute, and you'll see there's different values for these transient or quasi-static collisions. But again, just to reiterate, you have to consider both force and pressure for these type of collisions. So how much force and pressure is permitted, and where do these values come from? You can see from the table and the diagram that specific points of the body and that have been defined in the body model, even front and rear stated. And these were developed by the Fraunhofer in Germany. And I understand they were derived by getting people, probably students, looking for beer money and just poking and prodding them, and basically until they said it hurt. And then these values were recorded. Then they went on to define the specific spring constants for particular parts of the body when performing the tests. And the spring constants represent the flexibility of the body region. And they're based on the sensitivity or the fleshier or harder parts of the body, as we know we've got all over. But it's very important that when we're doing these tests, the correct spring constant is used, because if not, then it will cause incorrect test results. And we've got to document these again. It's all down to the documentation. So taking all this into account, they produced and defined a body model or body map. And this is where the value attributed to different body regions for both force and pressure. So you've got these columns down the side, you've got the body region, then the specific part area of that body region, and then we have the quasi-static values permitted for both force and then pressure. Alongside these, in the two columns on the right, are the values for transient contacts. And you'll see there's just a lot of number twos in there. And this basically means you can double that value, apart from any contact at head height. They can't be doubled. And you may even notice that the values under quasi-static are very, very low. So it's almost saying that we don't permit any head height contact. So collision measurements are not there just to define how fast you can move your robot. It also proves that you have considered and documented, as we discussed earlier. The documentation will allow you to reproduce these collisions, either in case of an accident or periodically, to prove the values haven't changed. And the changes could be due to modifications in the application, or materials or workpieces being used, or wear, mechanical wear in the components. So I suppose it's much like with light curtains, where HSG 180 states dependent on the performance level requirement, type 4 every 6 months, type 2 every 12 months. The frequency of the stop performance of the machine must be measured and proven to ensure the application is still safe. So you may consider it from a similar angle, but it'll also give you traceability. So in case of an accident, you can prove what you've done and how you justify that you had all the best intentions of producing a safe application. So there's plenty of kits out there. This is our Pilz kit, and we've developed it very early on. We've used it in many applications. But we can either come and deliver this service for you guys, or you can buy a kit yourself and get training on how to use it. So the kit basically is the PRMS measurement system, and this is what we use, let's say, to do the force and pressure measurement. So for the force measurement, you've got the measurement tool, the spring, and the evaluation software. So we have one load cell and we change the spring constants. I know there's other kits out there where you have a load cell complete with a spring for each of the different values. Just different ways of going about it, really. For the pressure measurement, there's like a measurement film and a scanner to develop that, and a calibration sheet. And again, it all talks back to the evaluation software which has been developed. So our force measurement tool is designed to represent the human body, and it has an absorption material on the top. So it's a foam rubber pad just to simulate skin. And as I said, we have one load cell with the interchangeable springs. And here's an example of what the test result would look like. So we've used the cushion of a lower arm in this case. You can see that red line, and this shows the limit values which it must remain under. And you can see the other line coming down, which represents the half a second where it has to have reduced. The hardest part of probably setting these up is making sure you have the correct position and the correct tools to accurately replicate the collision. And you've got to do a bit of have some experience to get this correct, and do a good bit of thinking about how you would do it. So this next slide just shows you a pass or a fail. And although both of them come down below the limits eventually, the top one does it within that half a second time, as the bottom one doesn't. You can see that blue line that goes through, and it takes more than half a second to come down. So that would, in this case, be a fail as per the requirements of the standard. So that's the force measurement. If we go on to the pressure, we have 3 different pads which we put on the top of the load cell, dependent on the different body parts. And these, we place them on there, and they're to replicate the harder or softer parts of the body. So this illustrates the body map where they would be used. So it looks at the A70, the black one is probably on the harder parts of the body, whereas the yellow one is the fleshier part. And on to the last part of the measurement process, the photographic film. This photographic film will be placed on top of the collision pad. And it's a 2-part piece which will allow the pressure to be measured and proven. So you'll see there's the A film and the C film. So the A film is coated with a layer of micro encapsulated colour forming material. And the C film is the colour developing material. So as we press on, the pressure applied, very small capsules will burst, as you can see in the diagram. It is very delicate, so you've got to be very cautious when placing this on, and you will get a different colour dependent upon the level of force, and this is what we will develop and measure against the chart. But if you aren't careful with the film and placing it on, even the smallest pressure can cause the capsules to burst. So, but what does the film tell us? It's the pressure intensity. And this can be reduced by good design again at the early stages. So no sharp edges, rounded edges. As you notice with the design of a cobot, they are generally rounder than an industrial robot. But the best way I suppose I could explain it would be like the drawing pin, how the principle of a drawing pin works. You can apply a lot of pressure to the flat side and push it into the surface. So you have a low pressure against your thumb. If you turn it round and you apply the same pressure, then you're just going to pierce your thumb. So that would be a higher pressure. And it's quite a simple concept really. But these are the things that should be considered when you're doing your design. And again, as we said, the challenge. So when carrying out the pressure measurements, the areas to pay attention to are the delicacy of the film and its sensitivity to moisture. So don't apply pressure before the collision, because you may burst some of the cells before you even get to the bit. So finally, to finalize the application, once all the analysis assessments, concept developments, designs are completed, the application was engineered and installed, and all the validation and verification has been completed, all that's left to do is to build a technical file, and you will put all this information into it, along with any other remaining specified requirements as detailed in either the machinery directive or supplier machinery safety regulations. Produce and sign the declaration of conformity, and affix the CE or UKCA plate, and that will be the process complete. So, but just again quickly, I suppose before we go, we did touch on during the presentation a couple of B standards, but there are a few more common B standards which we'll just run through very quickly before we go. So these ones that may apply, so especially 14118, which is the prevention of unexpected startup. When we spoke about interlocking devices before, we'll look at 14119, and you've got the technical report which backs that up, which talks about the series linking of fault-free contacts, probability of fault masking, gives you guidance on that. And it's probably pertinent to say there is a table in the back of there, table 1, with some guidance which talks about the reduction of diagnostic coverage based on the probability of fault masking. So if you're doing robot applications, as you may know, without any diagnostic coverage, you revert to a category 1 architecture, maximum performance level C. So that would be a big consideration in the robot applications, with the minimum requirement being PLD Cat 3. 14120 will be the guards. Again, we went through 13849s, parts 1 and 2. You've got to look at e-stops, two-hand control devices, minimum gaps, and yeah, so pressure sensitive protected devices in 13856, hydraulics, pneumatics, and all that sort of good stuff. 61496, which is the electrosensitive protective equipment, light curtains. That did change as well to say that type 2 devices as of 2015 will no longer allow you to achieve performance level D. They were reduced to PLC. So again, that is a consideration for robotic devices. So there are more. This was just a few. So yeah. So that's it from me today. So thank you for your attendance, everybody. Just to keep you informed of what else we've got coming up throughout the year, we've got our next one is Jason Reed, who's been answering your questions today, doing 14119 and interlocking devices. And then Mark Staples will be doing e-stops in May. Jason's back again for packaging machinery in June. You know, the pleasure of me again in July for 13855 and safe distances. Mark will be covering Pure in August, and then Alex Bryce will be doing CE marking in September, and Jason will be back for safe operating mode selections in October. So, as I said as well, you'll also be emailed a link to the recording, or you can find it on the GoToStage website. If you have a look for Pilz on there, you'll see all the other webinars we've broadcast over the last few years. And if you want a copy of the slides, please just request it in the questions. So if anybody out there also has any inquiries regarding today's content or any other machinery safety requirements for that matter, just I'll leave the webinar running for a few more minutes afterwards, just so you can request in the contacts and just ask the question in the toolbar. So that's it really. Thank you again, everyone, for your participation today, and I hope you all have a great weekend. Cheers, take care.
See ya.